afternoon. I'm John Laird. I've been a faculty member here for 33 years, lost count. I do research in artificial intelligence. A lot of it, I guess these days, would be called old school artificial intelligence, but I think there's still a role for it. So my talk today is going to cover a lot of ground. I'm going to talk about the title is for human-like AI, cognitive architecture, common model of cognition, and interactive task learning. It's going to try to cover a lot of the different work we do in my research group, but there's going to be parts of projects that are not covered. So I apologize to my students who I don't get to cover all of their material. I'm also going to probably exaggerate or make unsubstantiated statements. Feel free to call me on them, and we can talk about them as I go along. I expect that people will have questions as we go along. So, and I'm trying to be a little controversial. So let's jump in. So I will claim that there's two dominant methodologies in artificial intelligence today. The first one is select a task or problem of interest. If you're in the medical system, you might say, I want to do something in order to help my patients in some way. Or if you're in an industry, you might want to find a way to do a process more efficiently. And so once you do that, you try to find a potentially relevant algorithm out there that can work on your problem. And today it seems like the potentially relevant algorithm is deep learning, but it doesn't have to be. You formulate the task for the algorithm. You then add knowledge to the system so that that algorithm can work on the problem, or you train the system on the problem. You then attempt to perform the task and the problem, and possibly this is a loop as it's training and performing it. And then you often manually refine or optimize the algorithm, and then you go back to either 2 and find, because your algorithm didn't turn out to be very good, and pick a new algorithm, or you go back to 4 and do some more training, or possibly you even, after you've done some refinement. So that's what I call, so in this case, what you're coming into the task with is you have a nail and you're looking for a hammer, right? You've got a problem and you're looking for the right tool to do it. The other one is going to be very much the contrapositive of this. You're going to develop an algorithm and use an existing algorithm. That's what you want to do. You want to figure out what's the best algorithm, what's an interesting algorithm. And so what you'll do is find a potentially relevant task or problem, and then you'll go through the same steps that we went through before. And so, come on, baby. And we just ran out of power. Or we ran, yes, here we go. And I apologize. And in that case, you have a hammer, some algorithm, and then you're looking for nails to test out your algorithm. Okay, so I see this as very task-oriented structure of the field is that it really looks at individual tasks, either from the algorithmic side, well, usually from an algorithmic side. Now, what happens is often a person is actually playing a very important role here. It's not like these systems are just autonomous and are going out and finding problems or developing algorithms on their own. In fact, we see that the human comes in at many different points along the way in order to make this whole process work. That's what keeps a lot of AI people employed, so that we have things to do. But it's not the case that we just have these AI systems that are going out there autonomously developing and on their own. So, the result of this process is that we have what I contend are very task-specific AI architectures. Systems that work on specific tasks, and even though there might be a general idea, say deep reinforcement learning, when you actually apply it to a problem, it has to be customized with hyperparameters and many other things in order so it can work on that specific task. So often we will customize the sensing, the representation it uses, and the processing and the learning. Sometimes we're using generic versions, but often we're doing a lot of customization. The advantage of this approach to what a human would do on a task are many. Often it's just improved efficiency over many dimensions. So often we can have faster perception and learning by eliminating distractors. We are focused on only a task, whereas a human coming into a similar task would be distracted by the fact that they're in a laboratory or they're doing other things. But the AI system only plays StarCraft. It doesn't get confused by the fact that it also every once in a while has to go and eat and do other things in its life. So it can be very focused on that. We also can have faster processing. By that I mean more focused processing, because we eliminate irrelevant reasoning. The system isn't reasoning about actually its hyperparameters probably or other things about its life. It's just working on that task, and maybe we can do faster learning by just focusing on a simple task. Also, in terms of the architecture, meaning the structure of how things all fit together, we can optimize the size, structure, and content of the memories for the needs of the task. We can say that we need this many gigabytes or this kind of deep learning architecture for this task and not have to worry about that it's not going to be sufficient for some other task. We can really optimize for the task. Some disadvantages are the limits on generality and robustness. So often, these systems tend to overfit the task and maybe need to redesigned or retrained for small deviations. I do not know this as a fact, but as you probably heard, DeepMind has a system that plays StarCraft, and it plays it at Grandmaster level. It doesn't beat all humans, but it beats 99.5% or 98, I think it's 98.5% of humans when it plays against them. But, and it trained for, I think, 200 years worth of human time. So it was as if you played StarCraft and did nothing else for 200 years. I would think you would be at the top 1.5% as well, if you were still alive. But if we change StarCraft a little bit, I would bet that this system would have a lot of trouble, because it has found the optimal strategy for that collections of rules in StarCraft. We also don't see a lot of integration across multiple cognitive capabilities. We see them focusing on only those capabilities needed for that task, and often there's still a lot of human involvement in it, expert level and human, to set the hyperparameters, to design the system from the beginning, to figure out how the training regime should work. All of these things are required for that to happen, which works out well for graduate students who are going into AI because they have a lot to do. I also think that we sometimes see transfer and reuse, but often we see limited because we're so overfitting to the data. So I would say that this ends up with powerful but sometimes brittle solutions to specific tasks and problems. In no way am I saying that this is not useful. This is a great thing for us to have this technology so that we can solve problems and have the world a better place. But it doesn't seem to me that it's going directly in the direction of human-like AI.
So how do you respond to DeepMind saying, well, they have this alpha whatever that does chess and Go and Shogi, and learns them all?
And it doesn't learn them all at the same time. It learns one,
right,
and then it learns another, and then it learns another, and it doesn't learn StarCraft.
Right.
And it doesn't know how to play tic-tac-toe.
Right.
And it requires a huge amount of energy, literally, in order to train all these things. So those are all great. That's great. But that's not the generality of humans. So to look at this point in more detail, we could say that we have little pinpoints in the space of all tasks for chess. We have Go. We have poker. We have StarCraft. Maybe it's a bigger star. Fortnite. It turns out there's AI systems that play the game Fortnite. If you don't know what Fortnite is, it's played by over 200 million people worldwide. So it is a pretty popular game. And there are AI systems that play Fortnite, but they don't play it at, I don't think, expert level yet. Of course, they keep changing Fortnite out from underneath the AI, so that causes them a little trouble. Jeopardy. I give them that a big star. I thought the abilities to win at Jeopardy was pretty big. Maybe we have an AI system that can detect money laundering. I was just coming up with some arbitrary other AI application that might be out there. Autonomous driving isn't filled in yet. I mean, when we do, that is going to be a very big star out in the sky, but it's not filled in yet. And teaching a graduate seminar, I would claim, maybe it's not as hard as, as autonomous driving, but it is a big star. So if you put all those together, you end up with a star field, and you think about this in terms of all the tasks that AI has ever done, you end up with something like this, I would claim. Individual stars, individual points. So let's go and look at human methodology. What's the methodology that humans use for tasks? Well, which tasks do they do? Well, tasks come and go in response to the environment, interaction with others, internal drives, and things like that. There's not the case that we have something that is saying, do this, well, it depends on your job. But beyond even your job, you're not just doing a task or doing a task. You're living your life, and that life has many different tasks. Well, which algorithms do we use for a task? Do we pick one algorithm and apply it to all tasks? I would claim no. I would claim that we use many different algorithms based on what knowledge we have. And that knowledge is the accumulation of our background common sense knowledge that comes from innate knowledge that we're born with, that we get through development. This has been called core knowledge about space and time and objects, things like instincts as well. Then over our lives, we have direct experience. In his talk at the open house, or the symposium, Satinder said that he thought that all learning can be done through experience. And that's possible, but that's not how humans do it. If that was the case, what in the world are you doing here, right? I mean, you're getting an experience of listening to me, but hopefully you're learning something from me that comes from my experience and from others' experience. And so when you read a book, you're getting information from others' experiences. And if you want to ask, what can you get from direct experience, imagine you by yourself on an island, and where would you get? I don't think you'd get to autonomous driving, okay? So there's a lot that we get from our interactions and communications with others that really we're able to leverage the experience of others because we have language and we have culture. So we have all these other things. So human experience is very different than what the experiences of our AI are. So I think a really interesting question is the deep mind strategy going to work? Is the way to get to human-like intelligence to do one task after another, and doing each one, maybe human level, but you have these individual things. But I think that the human architecture is not optimized for any one task. It's actually optimized for generality, continual learning, real-time use of massive knowledge about many different things, detecting regularities across levels of abstraction and robustness. So if we look at this as the AI view of tasks and how we do individually ones, this is based on 33 years of experience here at Michigan and other years. This is my map of what human level abilities are. So this is, your ability if you actually are a chess master. But you're not just a chess master. It also turns out that you're actually a very good sailor. But you're not so good as a kayaker and other things in life. So you actually have a spectrum of capabilities, but they bleed, it's not just single points. Anybody in this room, if we sat them down, I think, we could teach you to play StarCraft. You might not play it very well, but you could learn to play StarCraft, and so you could play it at a base level. So we have this more, much different configuration of what kind of task we can do than where we are going right now with AI. All right, so there's a little rant for you to try to get you to think a little bit about where AI is going and where humans are. So what is my hammer? Okay, gotta have a hammer. My hammer is sort of a Swiss Army knife, which is to say we don't have one technique. Instead, what we do is try to ask what is the underlying architecture of humans. And so, see if this works. So this is what we've come to call the common model of cognition. So the common model of cognition was developed by a group of us as to be a consensus of a community of researchers that are looking at how we model human behavior. It is based on a set of cognitive architectures, and I'll go through the basic structure in just a minute. But it's an abstract specification of human-like cognitive architecture. It itself is not a cognitive architecture. It's an abstract specification, and we can ask whether other cognitive architectures are consistent with it. And one of the things we're trying to do is create a community that continues to develop and evolve it and refine it and extend it. And that is worse than herding cats. So it's kind of going on in a fitful manner right now. I will say even that we're trying to raise money to do this. Okay, so we're trying to create a center to do some, to keep the activities going on the common model. So let's talk about what the common model is. The number one, it's a cognitive architecture are those things that you don't learn. It's the fixed computational structure underlying cognition. So it's a simple way to say it is it's what you're born with. And it may be that it doesn't include everything you're born with. So maybe we only have captured, right now we've only captured a subset of that. And there's probably a lot more structure there than what we have. But it has this basic structure. It has perception that feeds into a working memory. A working memory is what you're thinking about right now. It's your current, gosh, I'm going to stay away from the C word, if you know, well, the C word is consciousness. It's what you're currently thinking. It's the current. Well, that's what the C word means, okay? And so you also, from working memory, can initiate actions in the world. So that's the motor system, and the perceptual and the motor systems can be tied together. There's also long-term memories. This is your declarative long-term memory, and often in cognitive architectures, it's actually split into a semantic memory and an episodic memory. It also has a procedural memory. Now, this is not, so this is a very vanilla specification of a cognitive architecture, and it's consistent with very many, and that's the point. Try to find what's the consistent view of the field, refine it, and then we can talk. Then we can have arguments over the details, as opposed to every time somebody presents a cognitive architecture, they have to do this. So the origins of this go back 40 years. This basic kind of structure. Key aspect of it is there's these communicating modules. It's not just a pile of neurons. There's actual structure to the interfaces between these. So we get to be specific about how information flows between them and what processing goes on within each one. So another big thing is that there's no, you'll see there's no modules for Go, okay? There's no modules for planning. There's no modules for abductive reasoning. All of these types of activities we assume are done through a combination of procedural memory and long-term declarative knowledge. Okay, and that's so that if you have complex behavior, it's not that you have a complex module here that's doing it, it's actually the knowledge that you have leads to that complex behavior. In terms of trying to, as a scientific activity, we see the potential benefits of this is that we provide a coherent baseline so that when people are talking about what progress they're making, they always can compare it to this. And things about this might be wrong, but it will focus the discussion on what's right and what's wrong, or how people agree and disagree. Right now, you have to read everybody's paper all over again as, from the beginning, as opposed to saying, I'm going to start with the common model, and here's what my delta is off of that. It also can provide guidance in extending research on individual components and constructing intelligent applications, and it provides actually a testable theory for different structures and functions of the mind. And this is actually one of the surprising results, is that it does provide a testable theory. All right, so a little bit more about the common model structure and processes. There's these task-independent modules. There's a cognitive cycle that involves the communication between procedural memory and working memory. Procedural memory is always matching against working memory, and there's a cycle here that is about 50 milliseconds. So that means we can decompose human behavior into sequences of 50 milliseconds. Every decision you make, so that decisions are not happening any faster than 50 milliseconds in humans. So if I want to predict how long it's going to take you to do a task, I come up with a decomposition of what your different operations are. I add that number together, multiply it times 50 milliseconds, and that is how long it takes you to think something. Now to do a task, it also involves perception and action, and you can have theories of how long it takes to do that, so you can make predictions of how long it will take people to do different tasks. There's also, although there's that sequential bottleneck of 50 milliseconds, all the processing underneath that level is in parallel. Each of these is doing parallel processing on its own to do its functions, and these modules can be acting in parallel themselves. There's just a synchronization here with procedural memory at 50 milliseconds. And as I said before, the complex behavior arises from a sequence of independent cognitive cycles, and then for each one of these different memories, there are learning modules associated with them. Now, just to let the cat out of the bag, I do believe in humans, these are implemented in neurons, okay? So that's the case, but it's not undifferentiated neurons. It's also not just a single feed-forward deep learning network. You'll notice that there's a chance for cycles, and there's a chance for specialization in the kind of processing that goes on in each one of these. So the original impetus for the common model was us actually looking at Soar, ACT-R. So Soar is the architecture I've been working on. ACT-R is John Anderson and his associates. Sigma is from Paul Rosenblum. And we looked at about 16 different assumptions or claims they made about the structure of their architectures, which is there this kind of learning mechanism? Is there this kind of connection between these different parts? And if you go back to 1993, which is 25 years ago or so, you'll see that all the green says that at that time they agreed with what is in the common model. Anything red says that they disagreed with what's in the common model back in 1993. And blue means they agreed partially. And so if you get to here, it turns out that back in 1993, ACT-R had no theory at all about perception and action, so that's why it's all red. We had some, but it was sort of like, yeah, in theory we believe this, but we never had anything implemented. So implementation is a really important part of it. One of the surprising things is that if you go to 2016, just before we wrote this paper, you'll see that we now have essentially complete agreement on these. And I would say, when we say complete agreement, I'd say that's like 90% or 80% agreement. And so you can see that both Soar moved and ACT-R moved in different ways. And it wasn't because we said we want to be more like ACT-R, or ACT-R said we want to be more like Soar. We were driven in these ways by the kind of tasks we were implementing and the kind of research we were doing. I should say that with a semicolon because we did take a lot of inspiration for certain aspects of Soar from ACT-R at the time. So places where there were red boxes and we were saying, well, that's something we didn't have or we thought we needed, we often did look to ACT-R. I'm not sure ACT-R looked at us that much, but anyway, we ended up with this. Sigma came in and has still some disagreements. Part of that is when you talk about architecture, you're talking about those fixed aspects that are not being learned. And why do you care about whether something's architecture or not? Well, if something's in the architecture, number one, it can't be modified. Number two, it gets access to metadata. So if we have knowledge that is stored in long-term declarative memory, if we have architectural support for how we retrieve things, and that's done automatically by the system, there are processes underneath there that are keeping track of how recently and how frequently we saw these different things, and that is done very efficiently, and that is not open for the system itself to improve on. It can't learn how to retrieve things faster from long-term memory. That's a fixed thing. So there's some disagreement with Sigma, which they say, well, we're going to push that up a little bit higher, and there are going to be more things open to the system being reasoned about and less things in the architecture. So that's currently, part of research, which is people are exploring different hypotheses. But so it's pretty interesting that we've come to this point. And where are we? Interesting. Well, we'll see where we go. So can you do anything with this more than just have pretty boxes around and maybe you have meetings and people come and talk about, here's how I would do this aspect and how I would do that aspect. Well, if you take this seriously and you take these arrows as how data can flow through the mind, which means how it flows through the brain, then maybe you can map these aspects onto different parts of the brain. And so here is a mapping of these different boxes onto different parts of the brain. Now, one of the disturbing things is there's a lot of brain not covered by any box. So that kind of, makes you say, well, maybe there's something going on in people that we don't model. And we accept the fact that the common model is incomplete. Like you'll know what's this down here?
Cerebellum.
The cerebellum. We don't have any box over that. And the cerebellum has gone through a lot of changes. I mean, that's one of the primitive areas of the brain. And my understanding is that it covers a lot of timing for fine motor movements and fine perception. So that has not gotten incorporated into our common model, but it shows here's a place in the future where we have more work to be done. All right, so say we have this modeling on the brain. Well, what we can do is we can have people do tasks, and we can look to see what parts of the brain get lit up. Usually this is a bold response, which has to do with the uptake of sugar. And so we see as they're thinking about a task over time, where is the flow of information? Where does it start, and then where does it go over time as they're doing these different tasks? All right, so you're watching the flow of information, sort of like flow of water through pipes, okay? And this is looking at this for a task that's the Raven progressive matrices. This is often used as an intelligence test. People are supposed to say, okay, if this comes after that, and that comes after that, and this comes after this, and this comes, what should be here? And people have to figure it out. All right? So this is one task. All right, so what we can do from looking at brain scans is see how the information flows through the brain. And our model, the common model, makes predictions of what flows are possible and what flows aren't possible. Because if you go back, you'll see that you can't go directly from procedural memory to action. You can't go directly from long-term memory to action, or perception directly to long-term memory, and so on. And also you have double links between these. So I did not do this work. This was done by Andrea Stocco at University of Washington, which I find is amazing work. But what he did is well, in this case we have 4 different tasks that he took. And then he tried to look at how well does the common model explain those 4 tasks, and he looked at other possible configurations. So he looked at a fully connected graph, and he looked at a different structured graph, and actually more recently he's looked at other structures as well in terms of how components in the brain could be connected together. And shockingly, the common model actually is the best predictor of what those results are across those 4 tasks. Okay? So that doesn't mean it's right, but at least for now, it's a better explanation than these other models. All right. So now I'm going to switch gears and talk only about Soar. So Soar was originally developed when I was a graduate student at Carnegie Mellon. My advisor was Alan Newell, one of the giants in AI and cognitive science. My collaborator over the years has been Paul Rosenblum, who was also a graduate student at the same time and is now at USC. And a few years ago I wrote a book on it. But it started about back in 1981. So this is my joke, I've been working on my PhD thesis for many, many years, okay? Which is fun. So now I want to give you an idea of what is a cognitive architecture by having you do we're going to do a little parlor trick. I know some of you have done this before, but it just brings to the fore the fact that our brain is not just a homogeneous bunch of neurons. It's actually a lot of structure there, and we think about things in different ways. So most people are able to do this task. If you can't, it doesn't say anything bad about you, but imagine the word wow. Okay? Are you imagining those letters wow? Now, flip it upside down. When was the last time you saw the spouse of that person? Okay?
3 years ago.
3 years ago.
6 months.
So you have an answer, right? You know, so theoretically, you were able to figure this out. I bet no one ever told you to turn a word upside down in your mind before, and you were able to do it. So what's going on here? This is my simple view of how this all works. So this is Soar. Imagine the word wow. It's going to come in via audio perception, and I have only a vague model of how all this works. But this is sort of the high-level view of how this works in a cognitive architecture. Imagine the word wow comes into audio perception. You are able to recognize that as a word. You know, the phonemes are converted into word, and somehow you get the sound imagine wow into your working memory. You're then able to retrieve from semantic memory what those words actually are, that there's a symbol imagine and wow, and then you're able to access some procedural memory that knows how to take this and do something with it, okay? So procedural memory is always looking for things here, and it sees, oh, I've got this imagine command to me. I should do something with it. What does imagine mean? Oh, you know, I bet it means put it into my visual buffer, which is very interesting that you know what that means, but I think everybody was able to do it. So you put it into your visual buffer. And then along comes rotate. That comes in, we go off to semantic memory, your long-term memory. We come back, we get the symbol rotate, we go into procedural memory, and we use the skill rotate, which I don't know how you do this, but you are able to send a signal down to your visual spatial system and rotate that, and you get the word mom. And then that comes into, and then I ran out of PowerPoint, okay? But then that comes in to symbolic working memory. You're able to access semantic memory and get what mom is, okay? That it's a person. And you have identification of who that is. And then I said spouse of. And so you're going through this all again, and you have skills that say, oh, if somebody says something here, try to make that relation to semantic memory and do a retrieval on it. So you do spouse of mom, and you get back dad. And then you've got dad, and then I said, last time you talked to that person. And then your procedural knowledge is smart enough, whatever that means, to know that when I say the last time, you should take that and go access episodic memory. And you go into episodic memory and you pull in the last time you saw dad, and then you're able to actually create actions because you have to speak, and that requires more skills and more things, and out it comes as an action. And if I really wanted to do this, I could make a prediction of how long it would take you to do all those things, by how long it takes to go through each of these phases, access these different memories, and so on. And I doubt that it would be within 50 milliseconds, but I bet it would be within 50%, okay? No, I would get that kind of rough estimate. And so that's what a cognitive architecture is about. Now, we have not implemented this in Soar. It's beyond our capabilities yet, but it's the sort of thing we aspire to, okay? Just being able to have all these different, we do have all these different components. We just haven't gotten all of them singing together for this task. But I'll show you some of the things we did.
Yeah. So this one requires pure speculation. Fine. So is it you speculate that the engine that did well in Jeopardy would get that right or not?
Oh, it would not get that.
It would not. That's my guess, right?
Right, because number one, it can't go and find any previous. So one thing that the Jeopardy Watson
right.
was able to do was access a huge knowledge base.
Right.
And I specifically picked this as it being a unique set of actions that probably nobody has ever told anybody else to do.
Right.
So it can't find a memory of it in its system to then, and that there's no associations.
Right.
And
That's
specifically,
right.
it doesn't have a dad.
Right. Or even if you rephrase the question.
It's gonna have to come back and
even if you
say,
rephrase
I'm
the
so
question, though.
sorry, but I can't answer this question, I don't have a dad.
I mean, even if you rephrase it so it was a little more specific,
Right.
no, like, you know, the specific
Yes,
dad or
yes,
something, even then,
Yes.
it wouldn't have been able to do the imagine part, right?
Well, like, I don't think it couldn't do the rotate.
Right,
It couldn't do the historical imagine for its own.
right,
So part of this is it's a personal thing,
right.
and that's one of the things I wanted it to be as well. So it's not facts about the world, it's facts about yourself. Okay. So our methodology is to learn from and contribute to both natural and artificial data systems. So leveraging modeling and application, meaning psychological modeling, but also building applications to guide and evaluate development. So we really, our goal is to have both human-like and human-level intelligence at some point. Not getting there any day soon, but that's the point way out there that sort of drives it. So we're trying to avoid things that are significantly non-human, and we're not actually even trying to go anything superhuman. So we focus on the capabilities that are shared across the space of human tasks. We prioritize spanning the full range of capabilities over individual optimality or accuracy. So we do some research in cognitive architecture in terms of episodic memory. But we don't beat that to death and make sure that it models every aspect of human episodic memory. We get to the point where we've got something that gets pretty close, and then we start asking how does that interact with all the other systems that we put in. And because we find that one of the things that is unique about these cognitive architectures is when they can use all these different components together. And so we've done a lot of work on using those components as opposed to optimizing individual components. So it's really breadth versus depth. We try to minimize architectural structures. When we originally built Soar, it only had one learning mechanism, and we actually, rewrote a paper about how maybe that was sufficient, and we were so naive. I'm now very much more into that there are many memories, many learning mechanisms, but you learn by failure, okay? So we tried things out, we saw where it failed, and we moved on. So, but we still are very reluctant to add a new mechanism unless we have a lot of, say, evidence from neuropsychology that humans have independent mechanisms for those sorts of things. So adding a timing mechanism would be something I would take very seriously, given that we know that the cerebellum has a lot of these properties. And that's what happened when we added the mental imagery component that allowed us to turn things upside down. It was very clear that humans had that capability, and it was not something that was just implemented through other types of reasoning. So we try to always have a complete unified implementation. So there's one version of Soar out there. That's not true for ACT-R. ACT-R sort of, you could say a success of ACT-R has been people have re-implemented it multiple times, but that ends up to some divergence. So sometimes you wonder if a model done in one version of ACT-R would actually work in another version. And so whether all the assumptions people make are really compatible. So we try to look at large-scale hypotheses over the long term. So this is a
quick question on the second point you made. What are some of the examples for Soar to behave at a human level?
Well, why don't we see where we get to at the end of the song?
Sure.
Okay? Running out of time. Okay. So, history of Soar. Okay? This is going to be really fast. I don't think anybody in this room has seen the slide before. All right. So, we have, through the years, gone through many. So, this is back to 1980. So, 40 years. Starting with multiple tasks and multiple methods. That's what we started with Soar. And that was my thesis work. And then we try to do some general learning, interaction with the external environment, try to have systems that have lots of knowledge in them and cooperative behavior, task learning, more human cognitive capabilities, and what we've been focusing on a lot over the last couple of years is task learning, and we'll see examples of that. We had architectural mechanisms that were inspired by all of these, so over the years, as we did these things and went after these capabilities, we found we had to change and extend the architecture in order to have it be able to realize them. So there was a big thing that happened here where we suddenly decided to add a lot of new memories and systems. This was about 10 years ago now. And then here are some of the applications we've done. We did toy problems. We did a computer configuration problem. We did some early robotics work. And then we've done a lot, then we did synthetic flight and synthetic entities, and then we've done natural language and computer games and all sorts of stuff over the years. And so that sort of as to where we are now. So we've done a lot of different things over the years. All right, so as an alternative method to doing individual tasks, we actually are taking on the problem of doing task learning as a problem itself. So we call this interactive task learning, or ITL, where the system learns new tasks from situated interactive interaction. So this is you sitting down with the system and you leading it through a task, defining the task. This is not teaching it how to play chess better. This is teaching it how to play chess at all. Okay? That's the difference here. The system, so this would be, how do you learn the rules of the game? So the instructor and agent engage in natural language dialogue in a shared environment. The learning's online, one shot, and in real time, because that's how people learn, and that's what an instructor wants. So the way to think about this versus deep learning is that with deep learning, you have a lot of noise in your signal. You don't know what is good data. In this case, somebody who is telling you something you should learn, okay? So you learn in one shot, okay? And that's what a lot of our learning is. You don't go and take calculus 3,000 times. You take it once. You take each class once. And you take that curated data and you really take advantage of it. So in order to do this, we have to learn all elements of tasks. The generalize, the learn to other tasks and situations, and there is a bunch of pre-programmed knowledge in the system to get this far. So we've worked in mobile robot domains, and we've also had it work on over 60 puzzles and games. And it was supposed to show the robots. But it doesn't want to show the robots. All right, it's not going to show the robots. So the basic, yes?
Is the assumption here that the person teaching the task in this
Knows the task.
or is an expert of some kind?
Yeah, they know. Well, most of the tasks are not that complicated, okay? But yes, yes. So here's the basic learning process. The system is perceiving the environment. It requests instructions and say, tell me a new task. The person starts giving it the aspects of the task bit by bit in a shared environment, and some of the language refers to things in the world, and so it comprehends and grounds the language. If new words are used, it's going to ask for definition of those words. It constructs a representation of the task internally, stores it in semantic memory, and also then what we say is operationalizes the concepts, learns how to recognize those concepts in the world and how to process them efficiently. It then interprets that task representation and it compiles its declarative knowledge into procedural knowledge so it can execute it efficiently. It searches for a solution if it can. If it can't, it asks for help. So it asks for advice if it can't find a solution. And it does, once it finds a solution, it does a retrospective analysis of the solution in order to learn what we call control knowledge or policy, and then it acts in the environment. And then there's loops within here when it gets asked for new words and things like that. All of this is done, implemented, so this whole thing is implemented by rules in Soar. That's Soar's procedural knowledge. And that it knows how to comprehend language and do each of these steps. But in the background are Soar's learning mechanisms. These are not deliberate learning mechanisms. These are ones that are happening automatically as Soar is doing its processing. And that is how it does its learning. That's not completely true with semantic learning. There is deliberate storage in these situations of things getting stored into semantic knowledge. But all of these learning mechanisms are going on in the background. All right, so if you think of Soar and you ask, how does it start off for doing interactive task learning? This is all the knowledge that we pre-encode in the system. A lot of it, and sizes of boxes doesn't mean anything, okay? This is a lot of rule-based knowledge. This is a lot of facts about language. A lot of this is language knowledge. And there's a little bit of knowledge about spatial primitives that we can build off. Then we have our learning mechanisms on the side, and then through learning, we learn all this different kind of knowledge about these tasks. Some of it is action knowledge, policy knowledge, but the task structure and all of that is being learned as we interact with the human, right? So it's not just one type of knowledge or one type of thing. It's not just a policy. Okay, so we're going to talk real quickly about games. This is done by James Kirk. He just recently finished and is a postdoc right now, but not here. The reason we did games, one reason is they're really well defined. It's easy to tell whether the agent actually learns the correct knowledge. They're externally specified. We don't get to make up the rules of these games. So if something was hard for us to learn, we still have to learn it. Okay, so we don't get to choose what's going on. There's a lot of different kinds of concepts, actions, and goals. We need to learn new concepts that are a combination of primitives and learned concepts. And as we learn a new concept, that has to be able to be used in learning a further concept. So a lot of games use words that are only defined within the context of that game, or at least their meaning is grounded within the context of that game. So something like, I've captured a piece. That means a lot of different things in different games, but in each game it has a specific definition. All right, so where are we going with this? So these are the 60 games and puzzles that the system currently learns. There's a wide variety from simple board. These are all simple. I will say right off the bat, one of our challenges is if there's a lot of pieces, we don't have an attention model, so the system can get overwhelmed in processing perception or figuring out what the possible moves are. So all of these tasks are ones with small number of pieces, like under 10. Okay, just that that mean you can still play card games because the cards in your hand is much less than 10 usually. So we can play card games, we can play marking or logic puzzles like Sudoku, a small version of that, I don't know, stacking frogs, Tower of Hanoi, traveling salesman on small traveling salesmen, 5 puzzles, Sokoban, things like that. All right? So, I am going to run out of time. Okay, learn all aspects of a task. So there's different aspects of a task. We use the problem space formulation of tasks, which is hypothesized to be complete. And we can learn goals, we learn actions, we learn failure conditions, task-specific terms, such as if the locations have the same value, then they match in Sudoku. Might have a different definition in a different one. All the words that are underlined are things that had to be defined because the system, well, actually Toad didn't know, are things that have to be defined. And what would happen is you gave the instruction, the goal is that 3 of the captured locations are in a line, the system would say, well, what's captured? And then you would provide a definition of capture. And you'd have to ground it into things in the world. So, for example, one of the things is, here's the instructions without the system asking questions about how you would teach it tic-tac-toe. This is the instructions for 3 minutes Morse. Turns out you don't know this, but they're very similar. So if I teach tic-tac-toe and then I teach 3 minutes Morse, it turns out everything in green is exactly the same between the two. And so we want to be able to take advantage of that. So if we teach tic-tac-toe first and then we teach 3 minutes Morse, as soon as we say the name of the action is place block, then we can take advantage of what we taught it before. All right? In tic-tac-toe, we might have this version of tic-tac-toe where we're placing markers, blocks on a grid. We also might have a marking version of tic-tac-toe where we're actually making marks on a page. In this case, the goal is still the same, 3 in a row, and the goal is still that there's 3 captured locations, but what the different definition of captured is different for the different games. And similarly, what your actions are different for the different games. And you should be able to take advantage of this. It shouldn't be, I teach it tic-tac-toe this kind, and then, well, we're teaching it new tic-tac-toe. Let's start over from scratch. We want to be able to take advantage of this. So, notice this. Here, the definition of clear. If a location is not below an object, then it is clear. It says if the value of a location is absent, then the location is clear. So imagine we taught both of these. We end up with 2 definitions of clear. Keep that in mind. All right, so in order to evaluate this to see whether it can do transfer, we took 40 games, because that's what we had at the time, and then we made 1,000 randomly generated permutations of them. So we taught game tic-tac-toe first, and then all the other games after. Then we had one permutation where tic-tac-toe comes second, and then another permutation where tic-tac-toe comes 34th. But before that are going to be multiple permutations of the games that came before it. Okay, which games come before it or after. And we can ask, if we're getting the transfer I showed before, how many words does it take to teach the game based on its position in terms of having other games taught before it? Does that make sense? And this is what you get. All right, so what you see is this game taught the first time. It turns out this game is called Killer Sudoku. It is a combination of Ken-Ken and Sudoku. Never heard of it before. And it takes about 240 words to teach it. But because we teach Ken-Ken and we teach Sudoku, as we go along through random process, one of those games might be taught before it. And if they are both taught before it, by the end, it only takes us about 60 words to teach it, because we were able to take advantage of it. So what you're seeing is the decrease in terms of the number of words taken, because the probability that a game that has similar words in it increases as we go along. Now there's a few games that don't have very many words at all in common with anything else. Turns out this is Block's World, and it's so simple that the only concept it has in common with other ones is on, and that's almost in every other game. Okay? So we get one beat, and the same thing with Frogs and Toads. However, what happens when we have multiple versions of the same concept that could be confusing? So this is Frogs and Toads, a game you never knew. You can move a frog onto an empty lily pad, or you can jump over your partner to an empty lily pad. So in here we say if a frog is to the right of a clear location, then you can move the frog to the clear location. Well, guess what? Clear means two different things. It means either there's a clear location, there's no object there, or it means there's an absent value. That's actually what the definition for marking was. And both of those could be detected here. So what happens is the system underneath looks at the instructions, then does calculations to see how can it instantiate these instructions in the world it sees with the multiple definitions it has. And then it sees, are there any inconsistencies? And here in case, there is an ambiguity. And what it does is it says, oh, in one definition, there's one action. And the other definition, there's two. So it asks, how many actions are there? One or two? And that's an example of the kind of question it can ask, because it really does, I'm going to use this word very carefully, understands what clear means in that it can have two different definitions. Okay, and then it can ask a really insightful, what I would consider an insightful question. Because we want to avoid it saying things like, well, in Frogs and Toads, is clear mean that there's no object underneath it, or does it mean that there's an absent value or something like that? We thought this would be better. It could ask the other question. Anyway, so from these primitives, we end up learning a lot of words, okay, for those 60 tasks. All right, so I want to switch gears and talk about learning different tasks and different task formulations. In games, almost all games are goal-based tasks. I tell you a goal. You're supposed to win by checkmate, or you're supposed to get all the frogs on one side and all the toads on the other side. So there's a description of the final state. The great thing with goal-based tasks is you can do forward search, and you can try to find them. And that's what Soar will do, is it will try to search. However, sometimes we give tasks where it's easier to just take you step through it, such as cooking. If I tell you how to cook a cake, I don't tell you, well, the goal is to have a very tasty chocolate cake at the end, and given that you know everything about chemistry and physics, go for it, all right? It doesn't work that way. It's very difficult to figure out how much flour you should put together with how much sugar and baking powder and water in order to get that cake at the end, and how long to cook it. Instead, we don't do forward search for those tasks. We get instructions. So what Aaron has done is taken that problem and expanded Rosie so it can do goal-based tasks, procedural tasks, blended tasks, which means combinations of goals and procedures, and also hierarchical tasks, so that they can be decomposed into simpler parts. And I'm just going to cut to the chase. And he's also extended the kind of instructions you can get, because, and I'm just going to cut to the chase and go to the video, because the video is cool. for his advisor the video was cool, especially because he did it the night before I had to give a presentation, which is not today, but to a funder. Okay, so what we're going to look at is the task. It's called interior guard. This was a military funder. And what interior guard is meaning it's like patrolling a building, going around and checking on rooms and doing other sorts of things. The system's going to start and know nothing about interior guard. We're going to be doing this in a simulated environment. It's actually the April simulator. We're going to have a little robot that goes around, and we're going to instruct it on how to do interior guard. And it's going to work. It's not a live demo. Okay, so previously, we taught it a couple actions, how to move a plate onto a table, how to store the mustard, and how to fetch a specific thing. So it's learned tasks, and it's generalized them, so it actually knows how to fetch something. So we're going to start off in doing some instruction. So we say, go to the armory. And so can you all see that it's going to the armory? And, come on, how do I stop it? I guess that's how you stop it. We actually started out where we said, inspect the armory. And so now we're teaching it how to inspect the armory. And so this is a procedure-based task, because we're leading it through it. And so the first instruction we give, once it gets to the armory, we say, if a light switch is off, then turn it on. Come on, baby. And then we give it other instructions that are part of doing an inspection. So we say, if you are in the mess hall and a plate is on the table, then move the plate into the sink. If in the mess hall and a condiment is on the table, then store the condiment. And this is a little more interesting. If you are in a sentry post and an extinguisher is not present, then fetch an extinguisher from the supply group. Now I admit that teaching it all this while it's in the armory is kind of odd, and we're working so that these instructions are going to, in a future demo, will happen when we're in those rooms, but this is what happened at midnight, okay? If the location is empty, then turn off the light switch. So it turns off the light switch, you can't see it. And then it says, I'm ready for new tasks. And now we tell it another thing to do. So this is sort of a background task. While you're doing your interior guard, you know, if there's a fire, raise the alarm. Okay, so it says, okay, what do I do in order to raise the alarm? Well, remember the current location as the emergency location. Now, it's going to leave this location in order to raise the alarm. So it has to do some memory. So this is like it creating its own little variable called emergency location. And so the agent has that capability, and this is how we do it through language. Okay? And then go to the eastern hallway. So it goes to the eastern hallway. Wow, those were. And then what do I do next? Turn on the fire alarm. Goes and turns on the fire alarm. Go to the CEO's office, commander's office. All right, and tell the CEO, say there is a fire. There is a fire, it says. What is the next thing I should do? Say the emergency location. So now it has to, and it says the armory, so it has to dereference the emergency location and take the value and say that. It didn't say the emergency location, it said the armory. Okay, what do I do next? I'm going to teach you how to guard the barracks. The first step is to ask, who is my relieving officer? We tell them that officer is Officer Williams. Remember that answer as a relieving officer. So once again, repeat. Now repeat this until the relieving officer is present. Okay, we're now going to do a bunch of things that are part of interior guard. We're going to inspect the armory. What do I do next? Inspect the mess hall. What should happen when it gets to the mess hall?
Clean up.
It should turn on the lights, which we can't see, but it's going to turn on the lights. And then it's going to go and put away the ketchup, because we told it to do that. It's going to put the plate in the sink, because we told it to do that. And then it's going to say, okay, it's going to turn off the light switch, and now it's going to say, what should I do next? Now inspect the eastern sentry post. And then it's going to think about that for a minute. And so it's doing planning here all the time, you'll notice. Okay, it does know the topological layout, and it noticed there was no fire extinguisher there, so it went to fetch one. So it can so that's part of its task. And what do I do next? And so now you're done. You're done with getting the instruction on the whole interior guard. So now it's going to go off and do the individual steps. So now it's inspecting the armory, there was a fire there, it turned out. We had started a fire, so just to show that it knows what to do, it's going to raise the alarm. It's going to go and say, there is a fire, the armory. It's very terse. Now it's going to go back to inspecting the armory. Luckily, the fire is gone, and then it's going to inspect the mess hall, and Williams is there, and so, boom, we're done. So, we were able to teach all this from scratch through language, which, anyway, so, oops. No, come on, baby. And conclude, right? Oh, so Brian, I'm sorry, your stuff doesn't make it. Okay. He's one of my students. I was going to talk about his work for a minute, but we won't. Conclusion. So, I don't know. I think AI excels at specific tasks with lots of data and available computer resources, and still some significant human effort, and still a lot of money and time. Humans excel at a broad range of tasks, exploiting both general and specific knowledge and capabilities. I don't think that, so just because AIs aren't humans, we shouldn't feel like we failed. And I don't know that everybody should try to get to human level intelligence. It's very odd for me because 10 years ago, nobody was talking about human level intelligence, and now that's all everybody talks about. And I just find it disturbing because I think there's lots of AI that, I mean, we are seeing lots of people using AI for very targeted applications, and that's wonderful. But we don't need to create AI systems that are on the path to human level intelligence. That's what I want to do, but we don't all have to be doing it. Maybe it seems odd, but that's one of my conclusions. My personal bets on achieving human level AI, which I didn't talk about much, but I think it's got to involve a lot of cooperation, interaction, and learning from culture. It needs to have architecture similar to humans, which emphasize generality and diverse processing. But we still have a long way to go, and somebody gets some brownie points if they can tell what is unique about these three people.
Robots.
And what about them as robots? They are all robots that thought they were humans.
Okay.
So I just find that very intriguing.
Yes.
From Westworld, from Blade Runner, and from Battlestar Galactica. Okay, so.
Okay.
But we don't have to have this as our goal. All right? Science fiction can, but we don't have to. Anyway, that's the end of the talk. Questions?
Thank you.
Yeah.
Thank you, very interesting talk. I have a lot of questions, but I think the main one is how feasible you think is to transfer like that in a real world environment, given that my understanding is that its component is implemented, it has an underlying computational mechanism, and this mechanism introduces error that is accumulated in robot.
Why do you think that?
Because
Sorry,
why?
I shouldn't be challenging the audience. In our systems, that doesn't seem to be the case. As the system goes along, it is. So I didn't show you, but this works on 4 different robots. So the instruction system, although we showed it in simulation, it has worked on the fetch. It has worked on the April bots. It's worked on a arm with a Connect sensor, and it's actually worked on the little Cosmo robot. So we have got it onto real robots. The key thing, of course, is when you're doing sensing to have strategies in order to decrease uncertainty and decrease error. And so there is processing that we do as the perception is coming in order to try to get a very good, robust description of the system's environment. And if we do not have that, you're exactly right, that the system will start reasoning with incorrect knowledge and will make mistakes. But for the applications that we've worked on, we've been able to get sufficient, reliable, and accurate sensing so that it is able to perform those tasks.
So can I
Yeah.
follow? In how abstract environments this
So we had one of the April bots go up and down the hallway, didn't pick up things because it doesn't have an arm, delivering things to locations, and we have another robot, so that has a robot that has a hand that is able to stack blocks and does the Tower of Hanoi puzzle. I don't know. Let's see if I can get it to work this time. Well, this is really weird. All right, so here you're seeing one. I'm not going to fuss with it because it might not do the other. But here, he's giving commands to teach it how to go deliver something. And it does, we are not instructing it how to do the low-level navigation that was pre-programmed in by some of Ed's students. The other ones don't show up, but yeah, so you're right, we do need good perception. I agree.
Is it on your agenda for your agents to recognize the existence of other agents that may have their own goals and perhaps their own perceptions and actions?
Sure, yes. I mean, there have been implementations in Soar of systems that do joint coordinated maneuvers with other. So specifically, we did a lot of tactical air tasks where there's units of 4 planes flying together, and actually that builds up to about 15 planes together, and they're communicating using restricted natural language in order. They're not reading each other's minds, they're actually communicating via restricted natural language as somewhat similar to the way that humans do. I have to say similar because when humans get in tough situations, they swear a lot, and our agents never swore. So it did not have a robust natural language capability that humans have, but they were able to do coordination. There's nothing in the system right now that as sensory data is coming in, it's able to recognize or it's able to hypothesize that something's an agent given the kind of behavior it produces. So we have not done very much at all with activity recognition or that kind of lower level behavior. I'm hoping other people do a lot of that.
Anything about like theory of mind in the sense that
So a long time ago,
that another agent may not perceive something that I perceive.
so I'll tell you the best example that I know of.
Okay.
You heard of the game Quake?
Yeah.
So Quake is a game where you're an individual in it and you're running around trying to shoot other agents in it.
Right.
So we had something called the Quake bot, which played Quake. And what it would do is if it got into a situation where it saw the other player far enough away that it couldn't engage it right now, it would then create an internal model of that player and say, okay, given what I know about the world, and that means the different objects in the world, and in that game there's things called power-ups and other that you might go around and collect. So the system would say, well, given what I think its preferences are, I bet it's going to go over here in order to pick up the quad damage power-up. It would then go its own way and try to get there before it and set a ambush. And also, it would notice the other agent's behavior as to what things it picked up and what preferences it had, so it would build up an internal model of how the other agent's desires were different than its own. And then you play against it, and every once in a while, it only happens once in a while, you're coming out of a doorway, and it's sitting there ambushing you, and it freaks you out. So, but yeah, so that is possible to do in SOAR. We can have a representation of not only what the agent's beliefs are in working memory, but we can have a representation of what another agent's beliefs are in working memory, and then reason about those. Is that what you're looking for?
Sure. Very good.
So for a simple game like tic-tac-toe, which as I recall, if you go first and do the right stuff, you can't lose. You can't. So I didn't see any of that in there. Does it figure that out or not?
So it's doing internal search in order to play those games. Actually, for games, it has a very core theory of mind about the other player, so it only does one step look ahead for games. For many of those puzzles, it does multiple step look ahead. But the point is, we're emphasizing here is not to play the game well, but to play the game at all.
But I'm trying to say, will it get to the point where it can't lose in that case, or not?
If we gave it, if we let it search deeper, yeah, it would. I don't think it would discover the way it's today. It would not discover the generalities that you might, but a 3-year-old might not discover them either. I mean, you discover generalities like you should always move into the middle. This system would not discover that. It would not, so it won't make those leaps which require additional construction of internal representations that it's not taught. And so that's clearly, a research area. People back in the 80s did research in this area as well, and I think we should at some point try to exploit that as well. Yes?
Thank you, Prof. It's a great talk. I was wondering, like, for human, we learn by observing other people rather than getting specific instructions.
Well, I would argue that we do both. And when you learn tic-tac-toe for the first time, I bet somebody was verbally talking to you and showing you moves at the same time.
Yeah, so what happened after that? Say I've already learned tic-tac-toe and then I observe other people playing other games, then it might be that from my
So, have you ever played Settlers of Catan?
No.
Have you ever played...
I guess a lot of the answer would be no.
So what kinds of games have you played? Have you ever played a game where there's an instruction sheet?
Right, yeah.
Those games are very difficult to play by observation. So imagine trying to learn Monopoly by watching. Do you know Monopoly?
No.
Okay. Do you know backgammon? We're having trouble here. Chess. How about chess?
Yeah, that I know.
Okay, so imagine you're playing chess and you're just watching somebody play chess.
Right.
Now there's a lot you can learn from it, from observation, but there's also things that would be very difficult to learn from observation because they occur very rarely. So in chess, there's a move called castle, right?
Right.
When can you do a castle? You might not even know. I'm sorry, this is maybe, but turns out you can't castle if either your rook or your king has moved, nor can you castle if your king is under check or will be under check after the move, or the space that he moves through will be under check.
Right, I know.
Those things would all be very difficult, I think, to learn from observation.
Right.
So we want to take advantage of observation when we can. I agree completely.
Right.
But sometimes language is really good.
Yeah, do you agree? Is there
Do I agree what?
I definitely do agree that language is definitely the most important part. For example,
Let's say they're all important. I think when we start saying something's the most important part, a graduate student goes off and says, that's all I'm going to work on and I'm going to ignore everything else. Or a faculty member does. And there's a lot. And sometimes one thing's important, sometimes things are not. There's a lot of things where language is not important. There's a lot of activities we do where we don't talk while we're doing them. But there are some that it's critical. So I think you want to, if we're looking at how all the pieces fit together, you want all these pieces. Yeah, you get another question.
So something we do as humans is like we try, if we have multiple tasks to do, we try to prioritize. And sometimes that may be subjective of what is more important or not.
Right.
That is something that is taken into account.
So one of the things we can do is, thanks a lot, Ben. We can give it instructions to say, prefer doing this over that.
Okay.
We don't have, although we haven't used it within the context of this task learning agent, we do have a reinforcement learning mechanism that theoretically, if the system does have multiple tasks that it's doing and it is getting reward from the environment or internally, it would learn which tasks it should do at which time. Can't claim that it does because we haven't gone down that path yet, but we have the mechanisms in place to at least explore that. But you're right, that's an important part. Not only do we do individual tasks, but we sometimes switch back and forth between tasks. Sometimes we decide not to do a task because we have something more important to do. And so in the context of that little robot that was doing the patrol task, there was an implicit, the way the instruction ended up working is there was this implicit thing is if you see a fire, that's more important than doing the patrol. And that sort of just worked out because of the way we did the instruction. It should be possible for you to give instructions so you can tell it is more important or it's less important. Like if you see trash, don't go and clean, sometimes if there's a little trash in a room, yeah, it's great to go and pick it up and do it. But if there's a huge amount of trash and that's going to put you behind your schedule, then you shouldn't do it. So we don't have that, we haven't explored that yet. There was another question over here, or not? Yes?
Can you?
It works underwater.
Oh, does it? Oh, well, that was my question.
Oh, come on.
Can you recover?
She does research on underwater vehicles, right?
Not any.
Oh,
That's not me. I don't.
all right.
The arm robots
Oh,
are
okay.
good chat. But
I shouldn't try to embarrass the questioners. Okay.
that's okay. Can you recover from errors? Like, what if I'm looking at that robot? Like, what if I opened a door? Would you be able to say,
a lot of
okay,
that
that's
has
not
to
an
do with
interface?
the low-level navigation system.
Or what if,
So let me address the question. So there is no universal error recovery scheme in the system. I think that's an interesting question as to how to handle that. One of the things we haven't done, just to show how bad we are, is if we give bad instructions, we don't have a way to correct it. And that's one of the things we have to do. So, if we give it an instruction and we tell it to go make paper clips, and it starts grabbing everything in the world to make paper clips, we can't tell it, lay off the paper clips. So this is fine. This is like the Sorcerer's Apprentice. But I don't see that as a fundamental issue. I do think error recovery is a really important part to have in autonomous agents, but it's really hard to do it in a general way. Maybe I'm wrong, but I think a lot of error recovery is pretty, if it can, so some of the errors, if during execution the world changes in a way. So for example, we have this little hand robot that stacks blocks and does little games in front of it. And also I believe this would be true for the fetch. If when it picks up a block, it drops it, it will then automatically go and try to pick it up and recover. Just because the way the task knowledge is encoded, it knows that it's supposed to be doing that. So there's some errors that are just going to handle very easily, but anything that requires it reasoning outside of the space of capabilities that you've given it, it won't be able to handle. Whatever that means. So good. Actually, on our list of research topics is how to handle incorrect instructions and failures during instruction. All right, well, thank you all. Have a good evening. Let's get started.